Hello, my name is Gustavo Jamancalino. So I am very happy to be here, and today I will present a terrestrial method named geometallurgy and apply for the space exploration. I am from the beautiful Peru, and my background is in metallurgical engineering with a master in geometallurgy. And now I am studying a master program in space resources at Colorado School of Mines. So today I will present a geometallurgical approach of the exploration of lunar ilmenite. So geometallurgy maybe is a new concept for the people that are involved in the space industry, but in the terrestrial mining is a very common term in the last 10 years because geometallurgy is a new way to study a geological deposit. So in the past, when in terrestrial mining we find gold, so all the effort were concentrated to extract and process the gold like a one and homogeneous material. But the experience to many years in terrestrial mining so teach us about the different type of golds in the same deposit and different association with other minerals, with the ore itself, and maybe with the gangs and other materials. So, for example, in many mines around the world, in a specific geological deposit, you have 5 or 4 different types of gold in the rock associated with the specific rocks or maybe with different sizes. In this case, if you have a gold too small, you need a specific process. But if you have a too long gold, you need another process. And if you have a small gold, but inside of the mineral, you need a different process. So geometallurgy is the way to build a models based in identify a key and strategical mineralogical properties of the ore samples and linking them to predict the metallurgical repose. So we can study the deposit, identifying very specific materials, very specific characteristics of the ore, and we can predict how this process works with this type of mineral and what we need to expect when this mineral appearance will change along the time. So let me explain how we can apply this knowledge to the ilmenite on the moon. Ilmenite is a main candidate of the minerals to produce oxygen on the moon. So ilmenite is distributed in specific places named basalt mares on the moon, mare basalts. And the highest content in ilmenite around the moon is in mare tranquillitatis. We expect about 7 to 10% of ilmenite in the regolith. And many scientists designed a process to recovery and process ilmenite using magnetic separation, electrostatic separation, and reduction by gas that could be hydrogen, methane, or carbon monoxide. So many scientists worked, tested this process using simulate materials. But when we can apply this knowledge to the regolith samples, we have many challenges in the process. For that reason, it's necessary to identify which of the properties of the regolith could improve or could impact. Yeah, I think impact is the best term, could impact in the metallurgical repose, in the metallurgical results. So as we know, that comminution effect produced by impact of many meteorites, meteorites scratched by many years ago, the material producing a regolith with a very, very small size. I mean, 300 of microns. So regolith is a very fine material, and this is a good opportunity because we don't need crash or comminute the regolith for mining industry. But there is a problem with the minerals because the ilmenite is free in the rocks, but in the regolith is mixed with other materials. You can see the dots in blue color when I explain ilmenite free and ilmenite in basalt. So if we can measure how many ilmenite is free or is locked in a material, we can use a degree of liberation term that explain in a percentage how much ilmenite is free. When I say free, is ilmenite in one single particle. In the rocks, we can find values about 70%, 80% of a degree of liberation, but in the regolith is less, because as we can see in the red dots, the ilmenite in the regolith is mixed inside agglutinants or inside breccias or inside glasses, and it's very difficult. And this property impact in the metallurgical results, because if you want to apply, for example, in the test A and B, a magnetic separation, the magnetic separation has a limit in the regolith. You can increase the content of the ilmenite up to 24% in the regolith, no more. But in the rocks, the ilmenite from the rocks, you can increase up to 62%. So that means we can see this part that degree of liberation in the rocks is a benefit in comparison with the degree of liberation in the regolith. So to comprovate, we study another data about electrostatic separation with a simulant where the ilmenite is free with a degree of liberation almost 100%, and with the ilmenite in the regolith with a very low degree of liberation, around 40%. So as we can see, in that simulant, we can achieve almost 100%, almost pure ilmenite after the electrostatic process. But in the regolith, is the half, is almost 45%. And if we want to change the process or improve the techniques, all the results are saying we can obtain up to 50%, maybe no more beyond this point, because the principal problem is that ilmenite is mixed with other material, and to free these particles, we need to apply a very difficult milling technique, and that is not a very good option to apply in the moon, because the cost is very expensive. So we need to define and study the degree of liberation maybe in another range, like the rocks mixed, not the regolith, because maybe in the regolith, in the complete distribution, all the ilmenite has a very, very low degree of liberation. However, this specific important, as we know now, a degree of liberation index was not studied complete in the complete size distribution of the regolith. As we can see in the graph on the right, only in the blue part, we measure the specific degree of liberation. So we measure it in a range size range from 45 microns to 19 microns. So in this part, that represents about 20 or 30% of the size distribution of the regolith. We found about 50 degree of liberation. 50% of the ilmenite is free, and another one is locked in another particles. But what would happen if we measure in coarse particles? Maybe we can find interesting ore and materials for the process. So another important term is chemical composition of the ilmenite, because the ilmenite is not pure. So in the moon, the ilmenite is not free, the regolith, and is not pure. And there is a specific contaminant that is magnesium oxide, and magnesium oxide has a reverse correlation with the iron oxide. So when you have more magnesium oxide, the content of iron oxide decrease. And this is important for the ilmenite, because iron oxide is specifically this part that provides oxygen for the reaction. So ilmenite is oxide of iron with the oxide of titanium, but maybe these values of higher content of magnesium oxide in the ilmenite means another mineral named gehilite. So some phases of gehilite could appear in like very small dots in the ilmenites. So making this ore reducing the quality for the next process because we need ilmenite almost pure in grade and in the chemical composition itself. For example, if we simulate the reduction with hydrogen, using the thermodynamical framework for every reaction could occur, we need to reduce the free energy below zero. So we can achieve this increasing the temperature. For example, for the ilmenite, if we increase the temperature constantly up to 1000 degrees Celsius, we can start the reaction in the right direction, so producing water and after that oxygen. But if the mineral, if the ore is gay-chelite or the ilmenite has many content of oxide magnesium, the reaction will never happen. So as we can see in the graph, it's the same case if you use carbon monoxide, you can achieve the reaction with less temperature, 700 degrees Celsius, but with the gay-chelite, you need increase the temperature and the reaction will never happen. You need additional energy sources or energy or power sources to make the reaction, and that is very expensive. It's similar when you use the methane. So that means independent of these three methods with methane, with carbon monoxide, with hydrogen, the gay-chelite always is a problem. In the case particular of the methane, you can obtain the reaction when ilmenite pure up to 800%, but with gay-chelite, you need to have a temperature almost 2000 degrees Celsius. It's a lot of energy. So now we can understand how important is identify these specific variables. So we identified these variables in the sample from Apollo 11, but we need to identify the distribution and maybe the idea is, after this work, propose the idea to explore and add to the exploration of the lunar ilmenite these variables, magnesium dioxide and degree of liberation, to understand better the ilmenite deposit. Because as we know now, including factor of these two variables, oxide of magnesium and degree of liberation, we can identify places with high ilmenite for the typical and traditional method and available ilmenite content. Imagine if you have very high content of ilmenite, like 20% of content in the regolith, but all the ilmenite has a degree of liberation of 10%, no more. So we don't have actually available ilmenite content, and the process doesn't work. So it's the same if you have a very pure ilmenite concentrate, like 100%, and you can apply the pyrometallurgical process, but the content of magnesium is very high, like 20 or 30%, the final metallurgical repose and behavior will drop. So we need to consider maybe another sources of ilmenite, like rocks, to produce oxygen and improve the methods of concentration from the rocks. Maybe we can start analyzing, calculating the consumption of the simple crashing in one stage in analog rocks on the Earth, maybe in places like Hawaii, for example, to explore this addition to the traditional method. So, and for mining, we need to recalculate, as we explained before, the ilmenite presence as ilmenite available in the regolith. So we can understand, or we can use this example to study another minerals on the moon or another deposit. Actually, we can study this relation in the polar deposit of ice water on the moon. So because geometallurgy is a good way to understand better geological deposits. So the presentation is based in 2 publications that I showing now. So thank you so much for your time. My name is Gustavo Germán Calino. Thank you for your time today.